Here's an 8 by 8 board with two opposite corner squares removed. We want to place non-overlapping dominoes on this board, each domino taking up two squares, and we want to cover all the squares. Now, not every method of going about placing these dominoes is going to achieve this. Some methods might get stuck after some point. Now, it's not yet clear, but we'll see in this video that in fact, every method will get stuck at some point. This is an impossible task. But before we see why this is impossible, I want to talk a bit about impossible tasks in general. Specifically, I want to talk about how one can go about showing that a task is impossible. If I want to show something is possible, all I have to do is show that I can do it. But showing something is impossible is completely different. Like, there are so many ways of placing dominoes. How on earth am I going to show that none of them will work? I find it hard to find the right words to explain the feeling of coming up with an impossibility proof, or even seeing an impossibility proof unfold before your eyes. I guess it's best to let the proofs speak for themselves. After all, they have enthralled people for ages. I'm sure many viewers would already be familiar with some impossibility proofs. Just to make everything a bit more structured, let's focus on two fundamental aspects at play. In our domino question, we want to show it is impossible to cover all the squares if all we can use are non-overlapping dominoes. So here, our goal is to cover all the squares, and our set of strategies are basically ways to place dominoes. We want to show none of the strategies can achieve the goal. Now consider the statement that the square root of 2 is irrational. There's nothing obvious about this. The square root of 2 was an actual number people knew about, and for ages they looked for integers p and q such that p divided by q would be equal to the square root of 2. In other words, a strategy for them corresponded to choosing integers p and q, and their goal was for their p divided by q to be equal to the square root of 2. To prove that none of these strategies would work could be very daunting. There are infinitely many strategies. You'll have to show that none of them work. Yet shockingly, the ancient Greeks proved exactly that. No matter which of the strategies you pick, you can never achieve this goal. An even more striking impossibility result is Cantor's theorem, that says that the infinity of real numbers is genuinely larger than the infinity of natural numbers. Here, a strategy would be a way to map natural numbers to real numbers, and the goal is for every real number to be covered. Here, the possibilities are way more daunting. We can't even imagine how complicated some of these strategies could look like. Yet, what Cantor proved was that no matter what strategy you use, you cannot achieve the goal. So, how did they manage to prove this? The neatest thing to me about an impossibility proof is that it gives you an insight into the nature of these strategies, like a limitation that they all have. It gives you a foothold that lets you overcome the daunting number of strategies. It makes you feel mathematically powerful. To finish the proof, you need to show that the limitation stops it from achieving its goal. But even without that step, I have to admit that feeling of power is pretty awesome. The power doesn't even end there, because although you got the insight when trying to prove an impossibility result, that insight guides you and lets you find possibilities as well. So let's look at some insights. For the square root of 2 question, one might think that any successful strategies must have 2's appearing in them somehow. Once you formalize this with insight into how integers factor, and hence how fractions have reduced forms, you're ready to prove the impossibility result. And those insights would be helpful in understanding many other questions about integers. For Cantor's result, you might notice that every strategy can only set one real number for each natural number. Well, duh. But then you might notice that choosing a real number involves one choice for each natural number. This is enough freedom for you to be able to choose a real number that has not been mapped to. Again, this insight can stick with you to help you to use freedoms cleverly in other scenarios as well. Now let's get back to the original question. The proof is shockingly short, and I'm going to show it to you now. So skip this section if you don't want to see it. The way it was shown to me, we start with a very weird step, which is to color in this board like it's a chessboard. Surely coloring this board doesn't change anything about the question. But then you notice that both of the removed squares are of the same color. So this board has 32 black squares, but only 30 white squares. And every domino covers two adjacent squares, so each domino has to cover a white square and a black square. No matter how you place the dominoes, the number of black squares covered must be equal to the number of white squares covered. And so it's impossible to cover this board. Here the insight is really about square grids. It's that the squares in a grid can be colored black and white in such a way that each square has a different color from every square that is one step away from it. This insight later proved crucial for me to solve other questions that involve square grids, like this one that has been recently featured on Mind Your Decisions. I suggest you try it out yourself. Viewers of this channel might have already noticed that I really like when an insight from an impossibility result guides you to a possibility result. For example, in both hat puzzles that I made videos on, we start with an impossibility result. Then based on the insight from that, we guide ourselves to the best solution possible. I really recommend watching these videos for that aspect alone. The impossibility results in them are also very neat. By just being precise about what a strategy is, the pattern to them and the impossibility result falls right into our lap. Now, viewers of this channel might also know that this helpful insight magic doesn't always happen. The Graham-Pollock theorem is a really marvelous impossibility result about graphs. But the known proof doesn't leave me feeling like I've gained a usable insight about graphs that I can now use for other problems. I can't help but love the elegance of the proof, but it robs me of my power trip, and I hate that about it. Enough about that though. At the end of this video, I'll leave a tricky puzzle and an impossibility result for you to try solving. And if you can prove the impossibility result, I think that would lead you very easily to a solution for the puzzle. Now, before I give you this puzzle, I want to give you a glimpse into impossibility results in the land of computation, which is where I work. It's really a crazy situation here, and I think some of you might be interested in hearing about it. I'll obviously be leaving out a lot of the work that people have put in order for the field to get to such an interesting point. I'm optimizing for fun here, not for being representative. So here in the land of computation, the strategies are algorithms, and we want to make an impossibility statement like such and such a computational task is impossible to solve with a fast algorithm. Now, even simple looking algorithms can run for a long time, so fast algorithm shouldn't be confused with a short algorithm. By fast algorithm, we really mean a small number of steps of computation. For example, say your input is just 4 bits long. Here is an algorithm, which is just some steps of computation. By doing each step, we end up with an output bit. If you list out all possible 4-bit inputs, these are the respective output bits you'd get from this algorithm. As you might imagine, if you have a really small number of computational steps, the resulting output will be very simple. As for what a reasonable number of steps means, since our outputs are just 4 bits long, a reasonable number of steps would be something that's comparable to 4. It'll make more sense when we talk about n-bit inputs soon. But first, what is a computational task? That's really simple. It's just a mapping from inputs to outputs. Our algorithm here already gave us a mapping from inputs to outputs in this table. So we know that this specific computational task can indeed be solved by a fast algorithm. But of course, there are many other computational tasks. How many computational tasks are possible here? Well, each input gets two choices for what to map to, so that's 2 to the power 16 computational tasks. In general, if the input is n bits long, there are 2 to the power n computational tasks that we can consider. And if the input is n bits long, a reasonable amount of computation is something like n, or n squared, or some other not too large power of n. But that means the number of fast algorithms is then much smaller than 2 to the 2 to the n. So of the many computational tasks, although a few of them would be solved with just a few steps of computation, all of the many other computational tasks would not have fast algorithms that solve them. We call these hard tasks. So that's a brilliant start. All we did was some counting, and we've concluded that yes, most computational tasks are hard. But that's not the end of the story. The question we want to answer next is which computational tasks are hard. From what we just saw, we know that if we pick a computational task at random, it is extremely likely that it would be hard. But we would not know for sure that the specific one we generated is a hard task. We still have not found a single explicit computational task that we know for sure is hard. There's a humorous way in which computer scientists like to describe this search for a hard task when we already know that almost all computational tasks are hard. It's like searching for hay in a haystack. The difficulty here is in coming up with an impossibility result when our set of strategies are fast algorithms. I'm going to jump forward from the point this question was raised to when a major breakthrough was achieved by Alexander Rasparov. He found a computational task and proved, with a restriction on what computational steps were allowed, that you need unreasonably many computational steps to solve the task. This first breakthrough was decades ago, and if we could just prove the same thing without the restriction on what computational steps were allowed, we'd be done. And so, soon after that came another major result, just not the kind you'd expect. In this new result, Rasparov and Steven Rudich went meta and completely changed the scene. They analyzed what they were trying to do. They were looking for a limitation on fast algorithms that they could exploit. That is, take a look at simple tasks, by which I mean computational tasks that can be solved by fast algorithms. They wanted to find a pattern that simple tasks have that hard tasks might not have. If we can find such a pattern, we'd be in great shape. Of course, since we want to be able to find such a pattern, it's only natural that the pattern should be easy to compute. That is, if you give me a computational task, I can efficiently tell you whether it has the pattern or not. After all, if the pattern is some really complicated thing, how would we even come up with it in the first place? Since most functions are extremely complicated, it's also natural that a randomly chosen task would not satisfy the pattern. To prove an impossibility result, we would naturally want to find this kind of a pattern. And this is the point where they went meta. What are we trying to do? For us, a strategy is a pattern that is present in simple tasks, and that is easily computable. The strategy would work if random functions do not have this pattern. We would also want to find an explicit computational task that does not have this pattern, but let's even ignore that for now. What Rasparov and Rudich noted was that such a strategy is a bit problematic, because it clashes with what some other computer scientists are trying to do. You see, over in the field of pseudorandom number generators, people are trying to come up with fast algorithms that generate numbers. They want these numbers to be such that looking at these numbers, it should be hard for us to figure out that these numbers actually came from a fast algorithm instead of being chosen at random. So this whole endeavor is premised on the belief that there are fast algorithms that do not contain a pattern that would allow you to easily distinguish between it and a random function. And just to recall, the people looking for impossibility results are hoping to say that all fast algorithms have a pattern that would allow us to easily distinguish them from a random function. So clearly one of these sides is premising their efforts on a wrong belief. It isn't clear yet which side that is, but the majority of people think the pseudorandom number generators have reality on their side. In fact, some pseudorandom number generators are even built on hard computational tasks. For example, if this primes related task, which I've explained in English below, is indeed hard, then it gives rise to an actual pseudorandom number generator. But then, if you're looking for a natural proof that this task is hard, you cannot possibly succeed, because as soon as you show it is hard, you also show that a natural impossibility proof does not work. And hence, a natural impossibility proof for this task is itself impossible. If you want to prove that this task is hard, you need to come up with impossibility proofs that are not natural. This sure seems like a bummer, but this also makes every new result in this direction really interesting and significant. It's an exploration of unnatural territory. That's all I wanted to say about impossibility results in the land of computation. Now I'll go back to what I promised, a challenging puzzle and an impossibility result for you to prove. You're given 12 balls, each weighing 1 kilogram, except that one of them is actually slightly off. That one is either slightly lighter or slightly heavier. You're not told which ball it is and whether it is heavier or lighter. You are, however, given a balancing scale. You can put some of the balls on one side and some or all of the leftover balls on the other side. From the scale, you would be able to tell which side is heavier or if both sides are of equal weight. Based on that, you can make another weighing on the scale. And then based on the result of that, a third weighing. But that is all. You cannot do a fourth weighing, and at this point you have to have figured out which of the balls is not exactly 1 kilogram in weight, and also whether it is heavier or lighter than 1 kilogram. I had no idea how to solve this question when I saw it, but that all changed later when I had solved a related question. Suppose it's the same question, but instead of 12 balls, you had 14 balls. Then what I want you to prove is that there is no solution to this problem. No matter how you go about weighing the balls, there will be some off-weight ball that the three weighings will not be able to identify. If you're very precise about what a strategy is, then this problem is not so hard. And if you can manage that, you can prove that it's also impossible even if you had only 13 balls. And when you've done that as well, I think you would know exactly how to find the solution for the case with 12 balls. Try to put spoiler alerts if you're posting your solutions in the comments, and I'll see you next time I upload a video. Or you could upload a video and I can see you that way. In any case, goodbye for now.